Today we're going to review the idea of concavity, or concave up and concave down in the context of our graphs, as well as talk about the second derivative test, which is another way for us to identify relative extrema, so relative max or min. Just in this case, we would be using the second derivative. You'll be familiar with the idea of concavity because we talked about it last year in pre-calculus. So a definition of concavity just says we're concave up when our derivative is increasing on an interval, and we're concave down when it's decreasing on an interval. So if our slope is increasing, we're going to be concave up, and if our slope is decreasing, we're going to be concave down. That is the magnitude of the slope. So if we're thinking about a graph like this, right, we've got a steep negative slope there and then a less steep one. So let's say the slope here was -2. The slope here is -1/2. The slope here, +1/2. Right? These slopes are increasing, so it's concave up, whereas if I had the reverse, right, my slope here could be +2, +1/2, -1/2, -2, right? These ones, these tangent lines, these slopes are decreasing. So when they're increasing in magnitude, getting larger and positive, then we're going to have concave up. And when they're shrinking or getting smaller, we're going to have concave down. In the case of the context of our second derivative is positive when we have concave up and equal to 0 when we have a potential inflection point, and we're also concave down when we are negative. So to determine concavity on an interval for our graph, we're going to look at the second derivative, much like we did the first derivative in the last section. So we would set the second derivative equal to 0. Solving for x, we'll get our potential inflection points. Then we'd test those values using our second test x values on either side in our second derivative to determine if it's an inflection point. All right, it'll have to change sign in order to be an inflection point. And once we've done that, we'll be able to tell about concavity. So let's look at a graph to start, and then we'll talk a little bit about the second derivative test before doing an example analytically with an equation. So critical points are where my slope, or my first derivative, is equal to 0. So I've got -1, 1, and 3 on this graph, right? And then our inflection points are going to be where our second derivative is equal to 0 and our concavity changes. So you'll notice this section, I'm concave up, and then this section, I'm concave down. So I've got inflection points at x equals 0 and x equals 2. We could then consider our first derivative line like we did in the previous section. And now a second derivative line. So thinking about this then, let's do our concavity first. So I'm concave down before 0. Concave up between 0 and 2. And concave down afterward. So that would mean my second derivative is negative. At the potential inflection point, it's 0. In between, it's positive because I'm concave up. It's 0 again at my potential inflection point, and then I'm down, so it's negative. These are inflection points because it changes from negative to positive and positive to negative at those points, or it changes concavity. Then if we're thinking instead, let me get rid of this highlighting, maybe, if it'll let me. It would appear that it's not gonna, let me get rid of that highlighting. All right, well, that's unfortunate. So over here, if we look on the far left before we get to -1, we're going up, so we're increasing. Then from -1 until 1, we are decreasing. From 1 until 3, we are increasing. And after 3, we are decreasing. So first derivative is positive, first derivative is 0, first derivative is negative, first derivative is 0, first derivative is positive, first derivative is 0, first derivative is negative. So to recap, when we've got concave down, we're looking at a negative second derivative. Concave up, we're looking at a positive second derivative. Inflection points are where we change concavity, and at those points my second derivative will be 0. With regard to my first derivative, that's 0 at critical points where my tangent line slope is 0, and it's when slope is positive, my tangent line slope or my first derivative will be positive. When slope is negative, my tangent line slope or my first derivative will be negative. All right. Take a moment and write down the second derivative test. We've got now a second way of finding relative max and relative min. So the second way says that if we find the first derivative, figure out the critical point, then we just have to look at the value of the second derivative at that point, and we can say if it's a max or a min. So we're going to do all three techniques. So first we're going to figure out increasing and decreasing in concavity. So for that we have to look at our first derivative. And our second derivative. So set them equal to 0. When you solve this guy, you're going to get x equals positive or negative 4. When you solve this guy, you get x equals 0. So for the first derivative, this is increasing and decreasing. Right, so we're going to have to test values on either side of positive and negative 4. So I could choose negative 5. And when you do that, you would get 25 times 375 minus 48, 27. So this is positive. So we've got increasing, our first derivative is positive. This is an possible max or min, a critical point, so they're going to have a first derivative of 0. Then we have to pick one in between, so I'll do 0. So that means I'm decreasing because my first derivative is negative. I messed up my sign here. That should be greater than 0. And then we have to choose a point on the right. So this is going to be increasing, and our first derivative is positive. Our second derivative, we've got that 1 point, possible inflection point at 0. So now we're looking at the second derivative. We pick a value on each side. So I could pick negative 1 and 1. So my second derivative is negative. My second derivative's positive, so I'm concave up and concave down. It switches, so that means this point here, x equals 0, right, is an inflection point because it switches. All right. Using the first derivative test, identify if it's a relative max, relative min, or neither. So at x equals -4, the first derivative switches from positive to negative, which means we've got a relative max. If we want to think about it graphically, right, we're going from a positive first derivative to a negative first derivative, so we are turning around and we're going back down, so we got a max. Then x equals 4, our derivative switches from negative to positive. So we've got a relative min. And if we're thinking about it graphically, we're going down because it's a negative first derivative and then going up. So relative min. All right, the second derivative test says we take our critical points. So we got x equals -4 and x equals 4. And we sub into our second derivative. And once we've done that, we look at the sign. So at this critical point, x equals -4, we're concave down. And at x equals 4, we're concave up, right? So we can just draw that. Concave up critical point would be a relative min. Concave down critical point would be a relative max. So it's another way to get to the same spot. All right, give the practice problem a go, and then do the one to turn in, please.